Okay, well, let's take a look now and get an idea of really what I'm talking about when I talk about where you've had different stages of deposition of different incised valley deposits. So we'll start out at time 1, we'll call it. We'll call this time 1. It's supposed to be a 1. And sea level will be falling, so we're carving out an incised valley. And let me put that in terms of this upper diagram now. Okay, at time 1, we have sea level falling. And so we carve out this valley. And at time 2, we'll call this time 2 here. That's the time where you're getting the marine transgression, so you're filling that valley with sediments at time 2. And so here's just kind of a general cartoon to illustrate that. Now in reality, this might be the vertical stratigraphy, but this diagram is just very simplified. So at time 2, during the rise in sea level, okay, that's when you backfill the valley. Now let's say, let's keep going with this, and we have another cycle now of falling sea level. And what's going to happen now, we're going to carve out a new valley. Say one right here. During that falling stage, and then during the rising stage, we're going to backfill this valley. So through these 2 cycles, sea level cycles, we have deposited 2 incised valley fills. Now they're separate ages, and they're isolated. And one of the mistakes that is commonly made in this type of deposit, see if I've got a picture of that. One of the, if you, oh, yeah, okay, excuse me a second here. One of the common mistakes that is made is like if you drill a well here, this black line represents a well, this line here, and you get this sand body, you penetrate this incised valley fill, and you drill another well, and this one penetrates that valley and that one here. Sometimes they're misinterpreted to be either a fault, so that this is actually, people think this is actually one sand body, in this case that is connected, or going back here, again, one sand body that is just offset by a fault. But in reality, you often get this type of deposition where it's purely stratigraphic. There's no fault here. There's no connectivity between the 2 sand bodies. You're going to have a shale break representing high stand deposition. You're going to get a shale break here, which in this case would be this shelf mud that would have been deposited as sea level continued to rise. So let me make that point that I should have made before, that right about in this part of our sea level curve, let me back up, wait a minute here. get rid of all this stuff. Okay. On this part of the curve, that's when you would be likely to fill with the green material, kind of a lag deposit. And then you move up the curve a little bit more, and that's when you're likely to deposit on top of it the red deposit. And as you move up even more, you're then likely to get into the estuarine type deposits and deposit those. And then when you get up even higher, that's maybe the time you've filled that valley, but sea level is still rising, and so you deposit this shelf mud, which forms a very nice topsoil. And that would occur somewhere up here, perhaps. So this filling is sequential. It's sequential filling, and it forms a depositional sequence. So you want to know, or you want to be able to understand, or try to understand, when you've got these incised valleys and when you don't. And I'll use this little diagram as an example here. In this case, you might put a fault in here and say, well, this sand is the same as that sand, which is the same as that sand, but that would not be correct. In other words, different sand bodies deposited during different sea level cycles. Okay? Well, somebody asked a question during the break. How do you distinguish between incised valley deposits and just regular meandering channel deposits? And the answer to that was, first of all, the channel deposits are usually smaller than the valleys into which they sit. And that's illustrated by a data set right here, the dimensions of channels and valley fills. And just a single fluvial channel, this might be the dimensions, say 755 meters wide and thickness of 9 meters thick, something like that. Whereas the valley is a larger feature, has walls on it that you can see on seismic and elsewhere. And it might have, you see the mean width here is almost 10,000 feet, and the mean thickness is about 30 feet, or meters. And so there is the difference. Here you are walking in the Grand Canyon in the U.S., and you're walking inside a valley, a huge valley. Now, if you walk down to the bottom of that valley, there's going to be a river down there, and that'll have a channel. So that's kind of the difference between the channels and the valleys, is one of scale. Okay, nothing much to show on this one here. Okay, well, what I've shown you to this point are kind of cartoons of the incised valley. And now what I want to show you is more realistic, how internally complex these valleys can be. Or excuse me, the valley fill, the channel in the valley fill. So, falling sea level, you erode out the valley, and then during the ensuing rise in sea level, you start to backfill it. And at the bottom, you'll get fluvial deposits. And then as sea level rises, at some point, you will get marine waters moving into the valley. So you might have some tidal influence there, and then forming an estuary here, maybe a little mud flat there, and that would be the fill of the valley right up to this point here. Now, if sea level continues to rise after you've backfilled that valley, you'll get marine mudstone, open marine shales deposited on top, and occasionally you can get some of these what we call sand ridges, which can make good reservoirs. They will sit upon this unconformity surface that is shown in red. They are transgressive in nature, and they form during that marine transgression. They go from sand and then they grade up into open marine mudstone. So this would be more of a realistic picture of what you might get, and so that's going to give you a complex reservoir, one that you have to deal with, where to put your wells and so on. Well, how do you tell them? How do you can you recognize them on well logs? Well, one of the ways in which you can recognize these on well logs is when you get a well or two that has an anomalously high thickness. And here's a case here where we have a well right there that's got a very high thickness of sand, but the well adjacent to it has just a little sand and a little sand over there. So that makes you suspicious right there that you have one of these incised valleys that was carved into underlying shaly deposits from a previous high stand of sea level. So you had high stand deposition here, forming the mud. Then you had a drop in sea level, so you eroded out the mud in this area, and then during the rise in sea level you had backfilling of your valley to give you this sand body. Now here's a little one over here, not as thick, but again it's surrounded by shale. You've got shale on the side and shale on the top in this case, and on the bottom in this case, in that case. Now, one of the reasons these make fabulous reservoirs is because they're kind of encased in shale. They're encased in seal rock. You've got shale off to the side here. You've got shale off to the side there. You usually have shale down below, and you have shale on top. Okay, so you have shale on the side, shale below, and shale on top. So you've got kind of a perfect seal, so that through geological time, the oil or gas can get in there, but then it stays there and doesn't migrate out. And over geological time, but in human time, it can you can extract it then from the wellbore at a faster rate. Okay, well here you see two well logs, okay, and let's say we had core for each one of these well logs, and we determined that this sand body here was a fluvial sand, and this one here was a deltaic deposit. Well, before people understood the significance of these changes in sea level, a common interpretation would have been something like this. Okay, you've got a sand body, okay, on both wells. You've just got a fluvial deposit grading laterally into a delta deposit, and these are going to be connected across here. So that was a common interpretation that was made for many years until someone put together the concepts of sequence stratigraphy, where you added that time factor, and over geological time, what happened to the shoreline and the nature of erosion and deposition. So now, when we see something like this, we can suggest that it's probably something like that, where you've got older deltaic deposits or marine mud from a previous high stand cycle. You dropped sea level, you created the sequence boundary here, or erosion surface, then you rose sea level and deposited the incised valley fill. Okay, so they're not of the same age. Okay, this was the key point. They're not of the same age, and more importantly to reservoir development is that this is there's a good chance that this is a permeability barrier that is going to prevent communication of hydrocarbons across that barrier from one sand to the other. Okay. Now, if you went back to this old interpretation, did that, you'd say, well, the sands are continuous, so we get good connectivity across here. By this interpretation, you don't. You have a barrier here that is preventing migration or connectivity. Okay? These are all the things you got to know when you're working on fluvial deposits if you want to maximize your production in those types of deposits, which are quite common. We used to call these types, well, let me back up again. When we use this terminology, or when we use this sort of an interpretation, we used to call these fluvio-deltaic systems. The idea being you had part fluvial and part delta. The fluvial would have emptied out into marine waters where you might have a delta deposit forming. But now, with this interpretation, we now call these incised valley fills. And it's a fundamental difference in your connectivity, mainly. So one of the things you'd like to do is to know the ages of deposition of your sediments, because in this situation, if you had some fossils in here, for example, that you could age date, in this case, the fossil would be of the same age. If this were the case, if this were correct interpretation, the fossils here would be of the same age as the fossils here. Okay? And that's one of the clues. If you've got some fossils in your rocks, that'll tell you if you've got that connectivity. Whereas in this case here now, your fossils should be older fossils here and younger fossils here. In other words, deposited at a younger time frame. And that's one way, if you do have fossils available, that, or you can do that with the palynology in the non-marine environments that I talked about earlier this morning. So that's one way in which you can determine that if you've got an incised valley deposit or just a fluvio-deltaic system. When I point this out, I'm going to go back now to this picture, because I want to, this picture is a real example from a reservoir. And I want to point out again that you've got dominantly shale here, dominantly shale there. These are from the high stand part of a sea level cycle. And again, then you drop sea level, carved out the valley, and then on the rise you backfill that valley. And if sea level continued to rise after the backfill, then you get a marine shale on top. So you get that nice side seal, bottom seal, and top seal. And so the example I'm showing you right here is this example right there. Okay. Okay, well, I've been doing all the talking, and I've got an exercise. We'll start it before lunch and finish it after lunch, but let me give you some background information, and this is an exercise for you to do to figure out what type of deposits you have and where you might want to put your wells. This is strictly a well log and core project, no seismic involved at all. So the area is Colorado, the state of Colorado. The city of Denver is right located here. So, state of Colorado, city of Denver, right there. And there's this huge field there called the Denver-Wattenberg field. It's a huge gas field that contains within that field, it does have some oily reservoirs in it, but for the most part, it's a gas field. What I'm going to show you next is a part of that field kind of down in this area right about in here, just to give you an idea of what the field looks like. Well, red is gas and green is oil here, and so what you see is a lot of gas. This is just part of the field. A lot of gas and a lot of even a lot of small scattered gas fields within that larger Denver-Wattenberg field. But you also see green, which is oily, and you've got some green overlapping with the red here, and you've got some isolated patches of oil off to the sides. So that kind of sets up the regional geology for you. It's a very active and old field, has produced a lot of gas over the years and some oil. Okay, here's the cross section. Here's the cross section across the field. And I've colored in yellow the sand bodies that make up the reservoir, or one of the reservoirs in this field. And if you look closely, you'll see different shapes of those, of the log shapes of the, these are resistivity logs, but different shapes of the SP log. So here you see kind of a lens-like shape to the edge. Here you see kind of a blocky log pattern. Here you see kind of a cleaning upward log pattern. This is also kind of a cleaning up log pattern. And here you've got kind of cleaning upward, but then it kind of gets more blocky. So subtle but real differences in your log shapes. And how this is interpreted is where you have this blocky sort of pattern, that's going to be an incise valley fill. And the erosion surface upon which that fill sits might be something like this. Okay, something like that. So somewhere between this well and this well, you see the shape of your logs has changed. This cleaning upward pattern is very typical of high stand delta deposits. Okay, so you can say here, well, I've got high stand delta, some high stand delta, but here now this upper part, which is kind of blocky, is going to be another incise valley that was carved into the underlying high stand beds and then backfilled with sediment during the ensuing rise in sea level. So what you've got along this cross section then is one incise valley. Somewhere in that area, you've got another one somewhere there. You don't know the boundaries of either one, just that they're between the wells somewhere. And so that's the type of reservoir you've got. You can get some production out of the high stand delta deposits that are cleaning upward, but the best reservoirs are really these incise valley fills. So once again, I'll point out that in the olden days, people used to connect this up and say, well, this is a fluvio-deltaic system where you've got a fluvial deposit here and then the same age deposited kind of at the mouth of the river as a delta. But now, with our interpretations that are more realistic now that we know of now that we know about these incise valleys, we now can make what is the proper interpretation. That's an incise valley, and that surface of that valley is somewhere between the two wells. And one of the reasons this was discovered was that fossils found in here were older than fossils found in there. Okay? So that indicated that that sand body was not connected, was not of the same age, but a different type of sand body, deposited at different times. And the times would be during a high stand of sea level, where you form these deltaic deposits, and then the drop in sea level where you carve through the delta deposits, and then you backfilled on the ensuing rise in sea level. So blocky gamma log shape, cleaning upward log shape, they're different. They're subtle, but they're different. And very significant. Now the exercise we're going to do is this is the part of that Wattenberg field, or the green dasher, the Wattenberg field, or part of it, is superimposed on a structure contour map. And if you can read the contours here, we're getting shallower, or we're getting deeper as we go from here to there. So we're reaching the deeper part of our reservoir. Here's the axis, it's a syncline. So we're coming up structure now So then you're dipping that way, so we've got a nice bowl-shaped anticline, syncline. And these wells were drilled into it, as I'll point out now. Now, what I'm going to show you is a cross-section that goes from well number 2 to well number 3 to well number 4 to well number 5 and then to well number 6. And here's the cross-section. Well number 2, 3, 4, 5, 6. These logs, these are either SP or gamma ray logs, and you can see where a sand body is here. Draw that in. Sand body here, another one there. Sand body here. Sand body there, and a sand body there. What you probably can't see this, but if you've got your computer there, what are shown here are the IPs, or initial potential flow rates, and what you find here is gas in this well. You've got oil in this well. You've got oil and gas in that well. You've got oil in that well, and you've got oil and gas in that well. So you say to yourself, well, what's going on here? Why do you get that different distribution? Particularly because we go back now. If you look at your structured contours now, well number 2 is deeper than well number 3. Well number 3 is deeper than 4, and well number 4 is deeper than 5 though. Oh, here's 5. Shallower 5 and even shallower number 6. So your deepest well now is the one that has all gas. So that gives you a clue right there that something isn't quite right, because you've got gas at a deeper structural depth than you have oil in these other wells. So you know something's wrong. Well, this is just some instructions. I'll go through these with you. But again, just to iterate, well number 2 has gas. Well number 3 is oil. Well number 4 is oil plus gas. Well number 5 is oil. And well number 6 is oil plus gas. And what's happening is you're going from deepest to shallowest as you go that way. You're going from deepest to shallowest as you go from well 2 to well number 6. Deepest structurally, shallowest structurally. So something's not quite right here. So the exercise, we can start this after lunch. Uh-oh, got to put in a slide. Well, at lunchtime I'll put in a key slide that I forgot to put in here. But what I'm going to give you, the slide that I forgot to put in here was one that shows you core descriptions. Each one of these black vertical lines is where core was taken in each one of those wells. And after lunch, what I'll show you, or what I'll give you, is the core descriptions, and that may help you decide why you have this distribution of oil and gas. If you take your core descriptions, do a correlation, of your sand bodies from well to well, and that may help you determine why you've got that odd distribution of oil and gas. So why don't we break for lunch and start again at 2 o'clock.